remember being actually in the lab late at night and plugging the signals into a spectrum analyzer. I'd had it on the wrong one. And at some point, I hit the button and then boom, everything was there. Probably, 10,000 different little comb teeth or lasers lined up.
There are three key things that make this such a Colorado-specific story and technology. One is that, of course, it's based on frequency comb lasers, and the birthplace of the frequency comb was right here in Boulder, Colorado. The frequency comb that's at the heart of the spectrometer was originally demonstrated here in Boulder in 1999 by Jan Hall and his colleagues.
The idea was you could take these frequency combs, these novel lasers, you could use them to look for molecules in the air or in a cell. It's a little bit like if you get your box of Crayolas and you get 8,000 different colors of green, and then you've got another row that's 8,000 colors of blue-green, and then you got another row that's 8,000 colors of green-blue, right? And if you look at any two of those crayons that are right next to each other, you're not going to be able to really separate out which is which.
Methane's a greenhouse gas, so it absorbs in the infrared, and these lasers are emitting infrared light. We send the laser beams out over the open atmosphere, and then when the light comes back, we're looking for these very distinct wavelengths of light that are missing, and we know that that was absorbed by methane. The second piece is you have to have meteorological and weather inversions. We need to understand wind patterns and how gases are transported across the environment. And then finally, oil and gas infrastructure is our target, and we're sitting, just 20 miles away from the Denver-Julesburg Basin, which has 40,000 active wells and many companies that are interested in detecting methane.
The way industry traditionally goes about this is they have cameras, but they operate in the infrared. So some guy has to drive it out to each one of those wells and then arduously look at every one of those wells. And the effect of that is that every well, best case scenario was getting looked at once a year. From a climate and a local air quality issue, that's a big deal, and from a safety standpoint. And the oil companies as well. Natural gas is revenue for them. They don't want to vent it out into the atmosphere.
We took that case to the Department of Energy and said, look, we think there's a really nice pathway for this technology to make it out to industry. And so they gave us an additional grant that we've then used to found Longpath Technologies. This collaborative project on dual comb spectroscopy has been a wonderful collaboration between National Institute of Standards and Technology, University of Colorado Boulder, NOAA, the National Oceanic and Atmospheric Administration, and then a couple of institutes that are connected with the University of Colorado, which are CERES, as well as RACI.
It can fill a gap where there's nothing that exists right now. It can happily operate without anybody right there with it for months at a time. And that's an important part of the engineering. There's no cost reduction if the box can't sit there and operate on its own.
We're talking about a laser system that's over a mile away from a particular gas pad, and we're able to measure leaks that are down to just a quarter of the breathing rate of a human being. So it produces continuous, real-time leak data that they've never seen before.
It could very well be the most important thing I do in my career. When I look at things that I can do for my kids going forward, to do my part to try and mitigate some of these climate impacts is a pretty big deal.